So the next few videos, I'm going to use the example system from the previous video, which is where we have a donut-like disc, so a disc with a hole chopped out of it. The larger diameter here is equal to uppercase D, and the inner diameter here is equal to lowercase d. And the center of mass of this rigid body is located right here. This is CB. So center mass of this rigid body. Now, also like in the last example, we're going to imagine that this donut-like disc can rotate about point O, right? And so now let's just define some reference frames for this system. So first we define our fixed frame. In this case, I'm actually going to define it as A1 in the pointing downwards. And so we'll have A2 pointing in this direction. And then my B frame, so my B1 is going to point to the center mass of this object. And then my B2 frame is here. And then this angle between my B1 and A1 reference frames is theta. Next, we should also draw our free body diagram. So I'm just going to draw this right next to it. So let's draw the forces acting upon this rigid body. And so again, we can pivot at this point O. So we have one force that's acting, so this is our gravitational force, so mg, okay, that's acting in the A1 direction. We also have reaction forces. So we have again, think of it as a normal force. Here I'm just going to call it F1. We're going to go very generic here. So I'm going to call this F1. And we're going to assume that this rotation is not frictionless. So actually I'm going to put F2 here. And so these are the forces that are acting upon the rigid body. And in this example video, I'm going to show you how to use the torque equation about the instantaneous center of rotation in order to get the equation of motion for this rigid body here. So if you recall, the torque of our body B about the instantaneous center of rotation is equal to moment of inertia about the instantaneous center of rotation multiplied by the acceleration of our rigid body, so B in frame A, right? And so for rigid bodies, unlike particles, rigid bodies have an orientation. So we pretty much always assign a frame to our rigid body. In this case, that's frame B, as drawn here. Okay, so the torque, let's focus on this term here. So here we have the torque of our body at our instantaneous center of rotation. And in order to calculate this, we first have to identify our instantaneous center of rotation. Well, as I've mentioned, or it's probably obvious at this point, that is going to be our point O. Right? At this point here is on the rigid body is not moving with respect to our inertial frame A. And so therefore it is the instantaneous center of rotation. Whole rigid body is moving about that point. That specific point doesn't move. So that means that we can write, we're ultimately going to calculate the torque of the rigid body about point O. so that means, so torque, we remember, is the cross product between a position vector and a force vector. So the position vector is going to be from our point O to the center mass of the body, CB, crossed with the force acting on the, capital F, acting upon the center mass of the body. And so this distance here, so this position vector here, ROCB, is equal to d over 2 in the B1 direction, right? That gets us to the center of mass. And then the force, the only force that's acting upon the center of mass of our body is mg, gravitational force. So we cross that with mg, and that's operating in the A1 direction. And so this then gives us, well, first to take this cross product, we have to take B1 and write it in terms of A1 and A2. And so that means we get d over 2 is equal to cosine theta A1 plus sine theta A2 crossed with mg A1. We know this first term here, that's going to go to 0, so all we need to calculate is d over 2 sine theta, and then we can put the mg over here, and then because this is A2 crossed with A1, this becomes negative. So we have negative A3. And let me just write that in a just slightly better. So we get negative mg d over 2 sine theta A3. Now going back to our equation, we already know what our moment of inertia about point O is. We calculated that in the last example. And then this acceleration term, right, is equal to theta double dot B3, or alternatively, you can write that as theta double dot A3. So we pretty much just now plug everything into this equation. So we end up, so T, right, is mg d over 2 sine theta, I'll put A3, is equal to, and so you can refer back to your notes, but this is equal to m over 8 3d squared plus little d squared times now theta double dot A3. So now we just cancel out some terms and simplify. So we can first get rid of m's, and we can get rid of A3s. We can also get rid of this 2 here and turn that into A4. And so now we can write this, pop everything over on one side, so we get 3d squared plus little d squared times theta double dot over 4, and then this term becomes a plus because we're moving it over, so then we get plus gd sine theta equals 0. And that is our equation of motion. So in the following video, I'll show you how we can calculate the equation of motion when we're using the equation that has torque about the center of mass of this donut.